We're going to start the most confusing module of this course, which is set theory. We've already talked quite a lot about sets. So when we were talking about graphs, we had a set of vertices and a set of edges. When we were talking about numbers, of course, we had the set of natural numbers, which we kind of formally defined. And we had the set of integers and so on. But what is a set? That's the question that we want to focus on today. So historically, the way this worked was that you would just have some rules for creating sets, similar to the same way that we defined this idea of natural numbers. We used Peano's axioms. We just had rules for creating natural numbers. We had two rules. It was that 0 is a natural number, and if I have a natural number, I can take its successor, right? And then we also kind of added a third rule, which said that these are all the natural numbers, so you cannot obtain any natural number by any other way, right? So we had some axiomatic rules basically on what we can do with natural numbers. But now suppose that I want to have similar rules to define what's a set, okay? Now, one of the rules that was historically used and led to a lot of problems is what we call naive comprehension. Okay. And the idea here is this. So comprehension means that I have some property and I can talk about the set of elements or the set of all things that have that property. Okay. And it's naive because it leads to a lot of paradoxes. So this is something that we have actually kind of done in this course already. So I can define a set by saying the set S is the set of all X such that some property of X is satisfied, such that phi of X. Okay, I've done this many times in this course, writing sets like this, right? So this is called comprehension. Basically, I have a property or a formula, and I have a variable here, some element or variable or item or thing, X, right? And then I'm saying, I'm looking at the set of all elements or things that satisfy this property. So suppose that I have this as an axiom for creating sets. So the same way that we had axioms for creating natural numbers, suppose that I take this comprehension as an axiom for creating sets, right? I can also have other axioms. Let's say I can say, well, I have the empty set, I have the set of natural numbers. I can have axioms that tell me if you have two sets, you can take their union, their intersection. I can basically create all of the normal operations that we do on sets. But suppose that I also have this. I want to show you that this will not work. So this comprehension is only good if I can write basically whatever property I want here for phi, right? So I don't have any limitation on what phi can be. And this leads to Russell's paradox. I forgot how many S's and how many L's again. Hopefully it's correct. Oh, I forgot how to write paradox. Okay. So here's the thing. Suppose that the property that I'm looking at is this. So suppose that phi of X is just the property that X is not a member of X. Okay. This is a property that makes sense. And honestly, for all the sets that we have seen so far, they were not members of themselves. Right? So if you look at the set of natural numbers, for example, it's not a member of itself. If you look at the empty set, it's not a member of itself because it doesn't have any members at all. Right? Okay. Fine. But where's the paradox? The paradox is this. I can define a set A containing all elements X that are not members of themselves. Okay. If I have comprehension, this is a formula. I'm just saying take all the elements or all the things that satisfy this formula. And that should give me a set. Okay, so I have a set A, which is the set of all X such that X is not in X. But now here's the paradox. I want to ask a question. The question is this. Is A in itself? Is A member of A? You see the problem with this. I'm either going to say yes or no, but both sides are going to take me to a paradox. So suppose that I say yes. Suppose A is a member of itself. What does that mean? That means that A is one of these X's which was not a member of itself. So basically, since A is in A, therefore A is not in A. Right? And that's definitely a paradox. But the same thing happens if I answer no. So if I say no, what do I mean? I mean, well, A is not in A. But A is supposed to be the set of all things that are not in themselves. So if A is not in A should be in A. And this is also a paradox. So you have no way around this. Basically, the problem we have is that we have to somehow say this set A does not exist. Because this is very similar to proof by contradiction, right? So we said that if we start with some assumption and then we get a contradiction, that's equivalent to proving that our assumption does not hold. What is the assumption that we started with here? It's the assumption that I have a set A defined by this formula. Okay, great. But now that I have this problem, what can I do about it? Well, I can no longer have this axiom. So this is problematic. I cannot do it. Okay. So this means that I have to go back and I have to give you axioms for sets. And I have to basically tell you what you can do with sets. And I have to make sure that the axioms that I create do not lead to any paradoxes like this. Okay. Now, there are many ways of axiomatizing set theory. The most common way of doing it is called ZFC. So this is named after two German mathematicians. This one is Zermelo. This one is Fraenkel. I think like this, I'm not sure. And C is just choice. It's the axiom of choice. And we will talk about them. We will talk about these axioms, not so much about the axiom of choice. For that, you have to take a course on set theory itself. But basically, the idea of these axioms is they tell you how to create new sets from existing sets. And they tell you what kind of operations you can do. But very importantly, unlike Peano's axioms for natural numbers, they don't give you a way of creating all the sets that can be created. Okay. So we're going to see what we mean by this. I want to follow the same order as this text here. So, okay, let's do this. We have the ZFC axioms. Okay, here's the first axiom. Well, I have a problem. Before writing my axioms, I have to have a language for writing things. Right? So before giving you my first axiom, I have to say what my language is. So I want to have a language in which I only talk about sets. So I don't have any other objects. The only objects that I have in my language are sets. And I'm going to call this language L. And I don't know how to write it. It's like this kind of L. It's too hard for me to write it, so I just write normal L. Okay. So the idea is that this is going to be a first order logic, which means that I'm going to have quantification. So in my language L, I support formulas that have these things. So my formulas can have logical operations. So I can have, or actually before that, let me define, yeah, I don't like this book. So let me do it this way. So first of all, I can have variables, and my variables are always going to be over sets. So I have variables. Let's show them by X, Y, Z, so on. And suppose that I have as many variables as I want. Okay. And then these are all going to be over sets. I have one particular relation. Well, I can't really call it a relation because I haven't defined relations yet. But I have one sign, one character, which is this, right? Belongs to, or is a member of, or whatever you want to call it. So basically, I can write things like X is a member of Y. Okay. This is the only sign that I have other than logical things. And then I have all the logical stuff. So I have the logical and Boolean operators. So these are things that we've seen at the very beginning of this course. So I have things like and, or, not, implication, if and only if, and so on. Okay. But we've seen that we don't really need all of them. It's enough to have, let's say, only and not, right? Because if I have and not, I can write all of the rest of them based on this, right? But I also have quantification. So I have for all, and I have exists. Again, it's enough to have one of them, because again, we've seen that if I have universal quantification and I just take the negation, that would be existential quantification and so on. But let's say that for now, I have all of them. And then the weird thing is people are so formal here, they would even tell you that we also have parentheses. Okay, so this language has parentheses. Now, I can spend 2 lectures telling you exactly how this language works, but you kind of know already, right? So you know how these things are going to work. I'm not going to actually teach you logic again. But basically, the idea is that I can have formulas like this. So I can say, for every X, there exists a Y such that Y is a member of X. I can write formulas like this. But whenever I have quantification, for example, whenever I say for every X, that means for every set X. So my quantification is always over sets. Okay. And whenever I say there exists Y, that also means there exists a set Y. And everything I have here are just sets. Okay. So other than this, I want to also have equality. So I want to have another sign, equals, which just says that 2 sets are equal. So this is my language. All I can write is that I can do quantification. I can write Boolean things, logical things, and I can use these 2 as my atomic expressions. I can say some set is a member of another set, or some set is equal to another set. Okay. So this is our language. And now, why was it so important to define this language? Because later on, I want to have some version of comprehension, and I want to say that you have a formula phi here, but I don't want to let you write whatever formula you want. So I want to limit what formulas you're writing. That's why I'm giving you a language, so that later on I can say you write a formula in this language. Okay. Now, finally, the axioms. ZFC axioms. So this is basically telling you what you can do with sets and how you can create new sets and so on. So we have axiom 1, and this is called extensionality. Now, I'm going to write my axioms in my language L as well, right? So first, let me tell you what it is in human language, and then I'll write it in L. It says that two sets are equal if and only if they have the same members, the same elements. Okay, two sets are equal if and only if they have the same elements. Okay. So I can write it in my language, right? In my logical language. You can write this like this. I can say for every x and every y, x is equal to y if and only if for every z, z is in x, if and only if z is in y. Okay, so this might get a little bit more complicated as we go forward. Well, not might, definitely gets more complicated. But basically everything is a set here. So even elements of sets are sets themselves. So that's why I can write for every z here. So basically I'm saying for every set x and for every set y, x is equal to y, if and only if for every set z, because we don't have anything other than sets. If z is an element of x, then z is an element of y and vice versa. Okay. This is fine. The first axiom is pretty obvious, something you've probably seen, not written like this, but definitely in some form in middle school. So this is the second axiom called the empty set axiom. Basically, it says that there is an empty set. The empty set exists. Okay. So we cannot prove that an empty set exists. We're just going to accept it as an axiom. So there is a set with no elements. How would I write it formally? I would say that there exists some set x such that for every y, y is not in x. Okay. And I'm using some syntactic sugar here because I didn't have this operator is not in. So this is actually the same as saying the negation of y is in x, right? So, but again, I prefer to write it in a way that is more readable. So this. There exists a set x such that for every y, y is not in x. Okay. We have two of our many axioms, but we can already prove something. Here's the theorem I want to prove. I want to prove that the empty set is unique. There is only one empty set. Okay, how would you prove this? So we say that there is a unique set with no elements. And at this point, I only have these two axioms. Yeah, so here's what I can do. I mean, I'm going to be super formal about this, but then we will get less formal when things get harder. So, because there's limited time in this class. So the first thing I can say is that I can use this second axiom to say that there is an empty set, right? So by this second axiom, by ZF2, there is a set X with no elements. Oh, and by the way, throughout this course, we always used capital letters for sets, but in this lecture, everything is sets. So if I want to only use capital letters, it doesn't really make much sense. So I use small letters for sets. So I know that there is a set that has no elements. Okay. I want to show that there is a unique one. So I say, suppose Y is also a set with no elements. Okay. Now, take any set Z. I can take whatever set Z I want, take Z. We know that Z is not in X, right? Because X has no elements. We know Z is not in X. But we also know that Z is not in Y because Y also didn't have any elements. So Z is also not in Y. Okay. So Z is not in X, Z is not in Y. So I can write this. I can write Z is in X if and only if Z is in Y. This holds. Right? Because if you look at one side, Z is in X, then Z is in Y. Well, there is no Z in X. So it holds vacuously. And if you look at the other side, that holds vacuously too. Okay. And this was for every Z. So what we just proved here is that for every Z, Z is in X if and only if Z is in Y, which by the first axiom means that X is equal to Y. So we proved that there is a unique empty set, and now we're going to give it a symbol. We're going to show it with the empty set symbol. So we show the empty sets like this. Okay. And by the way, now I can also use this symbol in my language L. Right? Because even though the empty set is not really part of my language, remember when I was writing stuff, I could only use these things, right? But I can just effectively add its definition to whatever formula I want, right? So suppose that I have a formula like this. I have a formula that says, whatever, for every X and for every Y, X intersection Y is empty. I mean, this is a stupid formula, but let's say I have this. And let's say that I somehow define the intersection as well, which is something we will do later. Okay. Now, this is technically not a formula in my language L because my language L did not have this symbol for empty set, right? But I can write this formula like this. I can say, well, there exists some empty set such that for every element Z, Z is not in the empty set, and this whole thing. For every X, for every Y, X intersect Y is empty set, right? So basically, I'm thinking of this empty set as a variable. If you want to give it a different name, I can give it like another name, let's say A. So there exists some A such that for every Z, Z is not in A, and then I have my original formula. So whenever I have a formula that has empty set in it, I can write it as an equivalent formula in L that doesn't have empty set in it. So I can think of the empty set as some sort of syntactic sugar as well. Okay, but actually let me keep all of my axioms together. So let me take this theorem and move it to the next page. Maybe it's this one. Okay. We've seen only two theorems, so on and so forth. And now we're going to see, sorry, we've seen only two axioms. We're going to see the third axiom, which is very simple. It's called the axiom of unordered pairs. So ZF3, unordered pair. Basically, this is what it says. It says if I have X and Y and they are two sets, then there is a set whose elements are exactly X and Y. Okay. So if X and Y are sets, there is a set, there is a unique set actually, but I don't have to write unique. There is a set, and we're going to write it like this, whose elements are exactly x and y. Again, it seems very trivial. I promise you it gets non-trivial really fast. How do I write this in my language, in my logical language? So this is how I would write it. I would say for every x and for every y, there exists some set z such that, well, I want to say that this z has exactly x and y as its elements. So I want to say that x is in z and y is in z. But I also want to say that it doesn't have any other elements. So I say, and for every other set w, if w is in z, then w is x or w is y. So you already see that things get complicated if you want to write them formally. Okay. But what does this tell you? This tells you that if you have basically two elements, you can put them together and create a set. But also, this axiom is not saying that x and y should be different. It says for every x and y. So I can have a case where x is equal to y. So I can take x and itself and make a set that has only one element, which is just x. Okay. So using this axiom and using the axioms before this, what are some of the things that I can create? I can create, so let me just put some pointer here. I have z of 3. So I know, well, I know that the empty set is a set. And now I have new ways of creating sets. So I can say both x and y are the empty sets. So that gives me the set that contains the empty set as only one element, right? So this is a set. Okay. But now I can take this one and the empty set, and I can create a set that contains these two sets as its elements. So I can say that empty set and set of empty set, this thing is a set, right? And I can continue like this. I can also, take x and y to be just this, and I can say this is a set. Hopefully, I always have the correct number of brackets. So you see, we already got to a point where we can create some sets. Right? Okay. But now, the problem is that, of course, in these sets, x and y are not ordered. Right? So if I have, let's say somehow magically I have numbers, then the set 1, 2 and the set 2, 1 is currently the same thing, right? So how do I create paired orders? Sorry, ordered pairs. Where am I? It's 9 a.m. Okay, how do I create ordered pairs? So basically, the problem is that I have two sets, x and y, and I want to define x and y and want to define what it means when I write the pair x, y. I want to give a definition to this. Okay. I'm not going to add a new axiom for ordered pairs. I already have an axiom for unordered pairs. So I'm just going to use that. And this is what I'm going to do. I'm going to say whenever I write the pair x, y, what I actually mean is the set that has two elements. One element is the set containing x, and the other element is the set with two elements, x, y. Okay. So this is how I define a pair. Now, first of all, for any x and any y, I can create this pair, right? Because I have x, So I can pair X with itself using the axiom, and I can get the set that only has X. And because I have X and Y, I can pair them together in an unordered way, and I can get the set that contains X and Y, and then I can pair those two sets together. So this exists. Okay. But now, of course, I want to have the main property, which says that two ordered pairs are equal if and only if their first components are equal and their second components are equal. So this is the theorem. I say this, I say let X, Y, A, B be sets. Now I want this. I want to say that the pair XY is equal to the pair AB if and only if X is equal to A and Y is equal to B. Now, again, this is one of those things that you didn't think would actually need a proof, right? We would actually use this as definition in most of this course. But at this point, I actually have a definition for what the pair XY means. The pair XY is this set. So it makes sense to say, well, when XY is equal to AB, then X should be equal to A and Y should be equal to B. And the proof is actually not as trivial as you think it would be. So here's my proof. I'm going to do a casework. Okay. So the first case is I'm going to check whether X is equal to Y. So case one, I say, consider the case where X is equal to Y. Okay. What is the pair XY in this case? The pair XY is just going to be, well, X, and then this one is going to have X and X, so it's just going to have X, right? So actually, let me write it out. So by definition, this is what the pair XY is when X and Y are the same. So actually, let me just write it as, oops. Why can't we have Linux? Okay, so this is the pair XX, which is the same as the pair XY, right? But then this second set here, I've written X twice, so it's just the same as the set that has X once. So this is the same as this. But then this whole thing is a set with two elements, but the two elements are the same again. So this is just what it is. So if you just follow the definitions, the pair XX is this weird thing. It's a set that has only one element, and that element is a set that has only one element, and that element is X. Okay. So in this case, suppose that this is equal to AB. So we have that this thing is equal to the pair AB. Right. Okay, I would love it if at this point I could say, well, look, the set on the left has one element, so the set on the right should also have one element. Right? But I don't have that. Right? All I have is my first axiom. My first axiom says that two sets are equal if and only if they have the same elements. Okay. So these two sets are equal, so they should have the same elements. Okay. But now look at this. I have this, the set containing A. It's an element of the right-hand side. Okay. So let me just call this the right-hand side and call this the left-hand side. This is an element of the right-hand side. So it has to be an element of the left-hand side. So this is in the left-hand side. But the only element of the left-hand side is X. So I should have that A is equal to X. Okay. But now I have to use my first axiom again. I have two sets that are equal. The only way that two sets are equal is if they have the same elements. So I take this A, which is an element of the left-hand side. It has to be an element of the right-hand side. So it has to be equal to X. I'm not going to write all of that down because I'm lazy. So just A equals X. Right. But then I can come back here and I can again say these two sets are equal. So if I take an element of the right-hand side, it has to be in the left-hand side. So the set AB is in the right-hand side, so it has to also be in the left-hand side, which means that the set AB is also equal to X. But then in this case, I now pick B. I say I have two sets that are equal. AB is equal to X. So I take B from the left-hand side. It has to also be in the right-hand side. So B has to be equal to X. Okay. So B is equal to X. But great. So I got everything I wanted, right? So I know that X is equal to Y, but now I have that X is equal to A and B as well. So I got that X is equal to Y is equal to A is equal to B. All of them are the same, right? And of course, I just needed this one. I just needed to say X is equal to A and Y is equal to. So in the case when X is equal to Y, I have a proof. This is just one of many cases. So I'm going to now consider another case, case 2. And I'm going to say this is the case where A is equal to B. So my first case was that my first pair has just one element, basically. My second case is that the second one has one element. But this proof is very similar to case 1. So just trust me. Trust me, it's case 1. Okay. Great. So what is our remaining case? So this is case 3. It's that X is not equal to Y. By the way, this is also syntactic sugar. It's the negation of X equals Y. And A is also not equal to B. Okay. Now I'm going to again do the same thing. I know that the pairs are equal. So I'm going to have this. I'm going to have X, X, Y. So this is the pair of X and Y. I have to close another one. Is equal to A and AB. Okay. So I want to prove that X is equal to A and Y is equal to B. So let's look at this left-hand side. I have this set containing X here. So it's an element of the left-hand side. The set containing X is in the left-hand side. Therefore, this set should also be in the right-hand side. Okay. So now this set is in the left-hand side. It has to also be in the right-hand side. So it has to be equal to either this set or this set. Now, another casework. I have one of these two cases. Either this set that only contains X is the same as the set that only contains A, or the set that contains X is the same as the set that contains A and B. Okay. In this first case, we write some more steps and X is equal to A, right? So this is just apply the same things again and again until you get that X is equal to A. So it's actually just one step, right? So A is a member of the right-hand side. It has to be a member of the left-hand side. A is equal to X. In this case, actually both A and B have to be equal to X, right? Because A is a member of the right-hand side. It has to be a member of the left-hand side. It has to be equal to X. The same thing for B. B is a member of the right. It has to be a member of the left. So in this case, I actually get that X is equal to A is equal to B, but this is a contradiction because remember, in my main casework, I'm in the case where A is not the same as B. I've already solved the case where A is equal to B. So this case never happens. And in this case, in the first case, I've proven that X is equal to A. Okay, so far I've proven that X is equal to A. But I still have to prove that Y is equal to B. Okay, so again, I do the same thing. I take this one, the second set XY in the left-hand side, and I say because it's a member of the left-hand side, and because the left-hand side is equal to the right-hand side, and because we have the axiom of extensionality, this should be a member of the right-hand side. Okay, so again, I have a casework. So either this thing that is a member of the right is equal to the set only containing A, or it's this other. So XY is equal to AB. Okay. If I'm in the first subcase, this means that X equals Y equals A. Right? This is a contradiction because I was assuming that X is not. So I'm definitely in the second subcase. XY has to be equal to AB. Okay. But what do I know? I know that X is equal to A, and I know that Y is not equal to X. Right? So X is equal to A, Y is not equal to X. So putting these two together, Y is not the same as A. Right? But Y is in the left-hand side, so Y has to be in the right-hand side. So Y is either A or B, but Y cannot be A, so Y is B. Okay, and this is again what I wanted to prove. Remember, I wanted to prove X is equal to A and Y is equal to B. I got X is equal to A here, and then I got Y is equal to. Okay, yeah, as you see, things are not easy. Okay. I promise not to do these kinds of proofs anymore. I will just give you the theorems and you can read them in the book or lecture notes if you want to, but no more proofs like this. Okay. So far, we can create unordered pairs, we can create ordered pairs. Now I want to talk about unions. And this is the axiom of union. So the fourth axiom of Zermelo Fraenkel. And this is weird. I'm going to give you a very weird union because I want to define union in a way that works for infinite sets. Okay, we haven't talked about infinity yet. We will at some point. But for now, the problem is that I don't want to just have two sets A and B and say I will have the union of A and B. I want to say that if I have a set of sets, I will have a union of all the sets in this set. Right. So basically, the important case is when it's an infinite set, right? So if I have an infinite set of sets, I can take the union of all of them. That's what I want to say. But again, I'm not going to use the language of infinity here because I haven't defined it yet. So what I'm going to say is this. I'm going to say if X is a set, then there is a set consisting of all the elements of X. And I didn't stutter. That's literally what I'm saying. If X is a set, there is a set consisting of all the elements of X. Okay. Let's write this formally. It means that suppose I have a set X. And remember that all I have is sets. So all the members of X, all the elements of X are also sets. I want to say there exists another set Y, and I want this Y to be the union of all the elements of X. Okay, but how can I write that? How can I write that Y is the union of all the elements of X? I can say that, well, let's say for every Z, Z is in Y, if and only if what? If and only if there exists some element W of X such that Z is in W. Did I close all of my paths? Again, this looks weird, but it's a very simple idea. It's this simple idea that suppose X is a set and it's going to contain some sets, 1, 2, 3, and let's say I have another set AB, and then I have another set. I don't want to put X itself there, so 3 or alpha. Okay, so let's say X is this. I'm saying there is a Y, and in this case, Y is just the union of all of these elements. So 1, 2, 3, A, B, alpha, beta. Okay, I'm saying there is a Y such that every element Z that is in Y is there because it was an element of some W. So for example, if this is my Z, then this is my W, such that W was in X. All I'm doing here is that I'm taking a union of all the sets that are members of X. So again, if X is a set, there is a set consisting of all the elements of all the elements of X. Great. So now I have union, and again, you can prove that these sets are unique, and also for this previous one. So here, when I said there is a set whose elements are exactly X and Y, there is a unique set, right? But uniqueness proofs are basically like this. They're not too interesting. You can write it on your own. And in this case, there's also a unique set. And the notation I'm going to use for this set is this. I'm going to write that Y is the union of X. So whenever I write something like this, it means that it's the union of all the elements. Okay. And of course, now we get the normal union that we know and love. So, okay, let's go here. I'm putting a line here. This is after ZF4. So let's say I want the union of two sets, A and B. So A union B, this the way that we normally use it. How can I write that? I can use this axiom. Well, I can use the previous axiom to create the set containing A and B. And then I can use this axiom to do the union of that set. And this is exactly what we normally just call a union. Yeah, so if I have two sets, their union is also a set, but I have something much better. I have that if I have a set of sets, the union of all the sets in this set is a set. Okay. Finally, we're ready for the one that actually matters, which is comprehension. So remember the idea in comprehension, and this is where we started with, was that I wanted to define a set based on some property or some formula. I wanted to say, let's look at the set of all the items or things or elements that satisfy some property. Okay, I already have a language for writing properties, but this is not enough to avoid the paradoxes that I had here, because if you look at this property, X is not in X, this property can be written in my language L, right? So if I just allow this kind of axiom, if I say that for every property that can be written in my language L, there is a set S of all the X's that satisfy that property, I will have the exact same paradox here. But what I can do is this. I can say, well, you can do comprehension, but you cannot do global comprehension. You cannot say the set of all sets that have some property. Instead, what you can do is, if you already have a set, if you've somehow constructed a set using the other axioms, for example, then you can say, I can take the set of elements of this set that have some particular property. Okay, so you should have some sort of a, let's call it universal set first. You have to first prove that that set exists. And then you can talk about the elements of that set. And you can say that I take the elements that have some property. Whereas here, we didn't have that, right? So we didn't have like a universal set here. This X could be anything. Or another way of looking at it is somehow this X is a set. So we can say that our universe is the set of all sets, but basically that doesn't exist. So what this paradox shows is that the set of all sets cannot exist. Okay. So how do I write comprehension? Well, I want to say that I have a formula. So I want to write something like this. If phi is a formula, and I'm going to say that this phi has some parameters. So let's say phi of z w1, w2 to wk is a formula, of course, in our language L, where the only free variables are basically z and w1 to wk. So I can evaluate this formula when I know z and w1 to wk. So with free variables, z w1 to wk. Now, what do I want to do? I want to say that, suppose I have a set. So let's say I have a set X, and suppose that I have k values w1 to wk. I can take all elements z of X that satisfy this. Okay, so if phi is a formula in L with these three variables, and X is a set, and actually, let's do it like this. And yeah, okay, and X is a set, and let's just write A1, A2 to AK are sets. Then I can have this set. I can have the set of all y's in X such that phi of y A1, A2 to AK. So this is a set. Again, this is just a very convoluted way of saying something really simple. All I'm saying is this: I have a formula and I have fixed values for all of the parameters here except for the first one, right? And what I'm saying is, suppose I have a set X. Oh, this was supposed to be small x. I have a set X. I can take all the elements in this set such that if I put that element as the first parameter to my formula, and then I put these constants as the next parameters, then the formula is satisfied. And this defines a set. So this is a limited version of the original comprehension that we had before. And this makes sure that I will not have the same kinds of paradoxes, right? Because now whenever I'm creating a set using comprehension, it's already a subset of a set that I had before, right? I'm starting with a set X and I'm saying, don't take all the y's that satisfy this phi, but only the y's in X that satisfy this phi, right? Okay. How do I write this axiom formally? So this is what I'm saying formally. I'm saying for every X, and for every A1, for every A2, so on to every AK, there exists a set, let's call it Z, such that y is in Z if and only if y is in X and phi of y A1 to AK holds. That's the formal axiom. Okay. But it's not really exactly one axiom, right? It's like an axiom scheme or a family of axioms, because I can use whatever value I want for phi and A1 to AKs and so on, and it tells me that this holds. Okay. But why don't I have the same problem as here? Why would I never get this problem? Yeah. So here's the thing. Let's say I have this A, but if I'm creating A by comprehension, the only way I can create it is if I already have a superset of A. If I have a B and then I say A is the subset of B that satisfies this condition, right? But I know that this leads to a contradiction, so this just means that this set A, this A is not a set, right? And it's of course also not a subset of any other set. So when I get a contradiction here, the result is not really that I have a contradiction. The result is that I just said, well, A is not a set, right? Because I don't have an axiom that tells me this A has to be a set. Not everything that you write is necessarily a set. So this is actually now, instead of Russell's paradox, it's no longer a paradox. It's just a proof that this thing is not a set. Okay, and similarly, you can prove that like you don't have a set of all sets. Oh, why can't you have a set of all sets? Actually, let's do this. Look, I know that this A is not a set, right? But what is A? A is like something that contains anything that is not in itself, right? If I had something that was the set of all sets, so suppose that B were the set of all sets, then I could just say that A is a subset of B. I could just write all X's in B such that X is not in X. And then I would have the exact same paradox, right? So I cannot have a set of all sets.
Why A is not fine? Why
But
A is not a fact? So why A?
No. What I'm saying is this. I'm saying suppose B is the set of all sets. Which is, by the way, something that I can write in my language, right? I can say that for every X, X is in B. This would say that B is a set of all sets, right? So suppose that B is the set of all sets. Then I could define A, instead of defining it like this, I could use my comprehension axiom and I could say this is the set of all X in B such that X is not in X. And then A should exist, because my comprehension axiom says that if I have a set B, I can do comprehension over B. But if A exists as a set, then I will have the same problem again, right? So I cannot have a set of all sets. Basically, what I just proved here, again, in the language of our, in our language L is this, it's that there is no set B such that for every set X, X is a member. Okay. So this is how we're avoiding the paradox. We don't have a paradox anymore. We just don't have this kind of sets. Okay. Here. So of course, all of these things are great. We are very happy. We proved that there is no set of all sets. But at this point, I can talk about something else. I can talk about what we call classes. So after ZF5, I can have a definition like this. I can say, this is my definition. I say a class is a collection of the form this. I'm going to say all x's such that they satisfy some formula x. I'm going to take that, and basically these x's range over all sets, and this formula is a formula in my language. But whenever I create something like this, so let's show it with big X, I'm no longer calling it a set. I'm calling it a class. Okay. Now, why does this matter? Who cares what I'm calling it? I just proved it doesn't exist, right? Now, I proved that it's not a set. Look, when we were talking about what we can do in our language, we said this. We said that in our language, we have these symbols. X is in y, x is equal to y. But I said that my variables are over sets. So when I'm using these symbols, I can only use them for sets, right? So, and when I'm writing a formula in this language L, my formula can use these symbols only on sets. Okay? So if I haven't proven that something is a set, there is no guarantee that I can use this on that thing. So again, I can have a class of all sets. So here's what I do. We usually show it with V. So let's say V is a class containing all sets, all x, such that whatever x is equal to x. So this just contains everything. Right? So this would not be a set, it would be a class. Now, why is this distinction important? Because again, it avoids Russell's paradox. So what was my comprehension rule here? I had this rule. I said that if I have a set X, I can use comprehension to find the subset containing elements of X that satisfy some formula. So by saying that this is no longer a set, by saying that it's a class, it means that I cannot apply comprehension. So I cannot write something like A is the set of all X's in V such that some formula X is not in X. This is a valid formula. This part is fine. This part is not fine because I can do comprehension only over sets and V is not a set. Okay. So I can still talk about the class of all sets, but it's just not something that I can use as a variable in my language. So I cannot use it in comprehension. I cannot use it to create new sets. Okay. But let's go back and let's continue talking about our axioms. So far, we have a bunch of nice axioms. I want to add another one because I want to get into defining things like functions and relations and so on. And surprisingly, the axiom that I need here is the power set axiom. So this is the F6 power set. Okay, basically it's that if you have a set, let's say you have a set X, then you will have another set that contains all of the subsets of X, right? So let X be a set. There is a set Y whose elements are subsets of X. But wait, we haven't defined subset. Okay. So in order to write this formally, I have to first give you a definition, a formal definition of subset in my language. Okay, so this is definition. Whenever I write A is a subset of B, what I actually mean is that for every Z, Z is in A implies that Z is in B. Okay. Again, this is syntactic sugar in the sense that I don't want to write this long formula, so I just write this short one instead. But the important point is that this long one is in my language L. So it's going to be a valid formula. I can write something like this. Okay, so now finally, my axiom, ZF6, is going to be something like this. I want to say for every X, there exists a Y such that for every Z, if Z is a subset of X, then Z is an element of Y. And if Z is an element of Y, then Z is a subset of X. Okay. Again, for keeping my sanity, it's really important to write this as two separate lines, but of course I could just write this thing here. Okay. Great, now I have the power set axiom. And again, you can work on this proving that it's unique and so on. I don't care for the notation. I'm just going to write something like this. I'm going to write that Y is P of X. Y is the power set of X. Okay. Now, look, when we defined ordered pairs, you would expect that the next thing we define is a Cartesian product, right? So when I defined ordered pairs here, I basically said that if I have, let's say, two elements X and Y, how can I create an ordered pair of X and Y? But then the next step would naturally be that, well, I have two sets X and Y, and I want to find the Cartesian product, right? So this is after CF6. Let's do Cartesian product, and let's see what happens here. And let's see why I'm doing it so late. Was it 6 or 7? 6. Yeah. Okay. So suppose that X and Y are sets. Okay. How do we normally define X times Y, the Cartesian product of X and Y? We would normally say that this is the set of all X, Y such that X is in X and Y is in Y. But do you see the problem with this?
First thing must be a big no comprehension.
Yes, exactly. We're doing comprehension, but we're doing naive comprehension. The thing that we saw gave us all those paradoxes. So I cannot do this. I have to say this X, Y, this pair should come from some set. Okay. And actually, to be honest, this is also not exactly the format that we had for comprehension, because the format we had for comprehension was something like this. Where is comprehension? It's like the set of all elements of some set. I couldn't really have a pair here. I could just have one element, right? But that part is fine because I can rewrite this like this. I can say X times Y is the set of all Z such that there exists X in X and there exists Y in Y such that Z is equal to the pair XY, right? So if I want to make sure I can write this thing in my language, I can write it like this. So now this part is a valid formula in my language L. But this part, I still have a problem with it. I have to have a kind of a universal set. I have to say where I'm taking Z from. And that's why I needed the power set. Okay, so here's the thing. what was our definition of the pair XY?
That's why.
Yes, so it's this. Okay. So suppose that I have big X and big Y, and suppose that small x is in big X and small y is in big Y. Okay. Let's just take the union of big X and big Y. So small x and small y are both going to be in the union of big X and big Y, right? But what does this mean? This means that the set that contains only small x and the set that contains x and y are both in the power set of the union of big X and big Y, right? Because, I mean, these two elements are in X union Y, so this set is in the power set of X union. Okay, so this one is in the power set of X union Y. This one is also in the power set of X union Y. So this one is in the power set of the power set of X union Y.
Oh,
Right? And because I have the power set axiom, and because I already have the union axiom, I know that I can have X union Y, I can have its power set, and then I can have its power set. So I can finally give a good definition for the Cartesian product of X and Y. I can say this is the set of all Z in the power set of the power set of X union Y, such that there exists some X in X and there exists some Y in Y, where Z is the pair XY. That was recorded. Yeah, this might seem weird again, but all of this is so that we can avoid Russell's paradox and also tons of other paradoxes. So it's not just Russell's paradox. Actually, when you have one paradox, you can have infinitely many paradoxes. Okay. There is actually a famous example of this, I think, from Russell himself. So he was saying that if you agree to a false statement or to a paradox, then you can deduce any other paradox from it. And then someone said, suppose 1 is equal to 2, prove that you are the Pope. And then Russell said, well, Pope and I are two people. 1 is equal to 2. So Pope and I are one person. So I am the Pope. So you can basically get whatever you want if you have a paradox. And this is just the same thing as saying false implies everything. So it's really important to avoid paradoxes. And we're doing all of this so that we make sure we have a system that doesn't have paradoxes in it. Okay. And again, very weirdly, in order to define Cartesian product, we didn't just need the definition of an ordered pair, which we already had much before. We also needed the definition of comprehension. So we needed the axiom of comprehension and the axiom of powers. Okay. But as soon as I have the Cartesian product, I can talk about relations and functions, right? And these are, again, normal things that I will not waste a lot of time on. So relations, what's this? A relation from X to Y is simply defined as a subset R of X times Y. Okay, so any subset of X times Y is a relation. Now I can also define a function. Oh, and also the notation I use here is that instead of saying that X and Y as a pair is in R, I would usually just write XRY. This is the normal notation that we use for relations. So what is a function? A function is a relation that maps every element of X to exactly one element of Y. So a relation R subset of x times y is a function from x to y, or we write it like this, function from x to y, if basically for every x, there exists a y such that x are y. So I want every x to be mapped to a y, right? And I don't here I don't need to say that x is in big X and y is in big Y, because I mean R is already a subset of big X times big R. But I can also write it like that. I can write for every x in X. But if I want to write something like this, this is equivalent to saying for every x, if x is in X, then something, right? So I can say if for every x in X, there exists a y in Y such that x are y, but I also want to say that this y is unique, right? So, and for every, let's say, z or y prime in Y, if x are y prime, then y is equal to y. So this is the definition of a function. And again, it's that intuitive idea that it's mapping every element of x to exactly one element of y. So I'm saying for every element of x, there is an element in y such that this x is mapped to it. And then I'm saying that, by the way, if there is something else that I'm mapped to, that something else is just the same as y. Okay. So up until this point, we successfully defined relations and functions, yes, and we can easily define one-to-one and onto functions here as well. That's just a simple thing that you can do on your own. But we've seen 6 of the 10 axioms, and soon it's going to get much more complicated. So I'll see you in the afternoon.